Hi and very good evening to all. First of all, I extend my gratitude to TFUG Hajipur, Anushka Raj, and other members for this esteemed opportunity to be a part of this session. I'm Rohit Narayan, a tech lead and senior deep learning engineer at Database. In today's session, we will discuss about how we can leverage the power of quantum computing into LLMs. Thanks for having me. In today's session, we will briefly talk about the basics of quantum computing as well as LLMs, and then we will discuss the challenges in LLMs with classical computing and how we can use the quantum computing in LLMs. After that, our main agenda will be to address some implementation challenges and ethical considerations along with the future trends that you will see in future with the quantum computing, and I will also show you a demo on how you can start your quantum journey with TensorFlow Quantum and demo on quantum transfer learning using our existing resources without the need of any quantum computer right now. Okay, so interesting. So let's get started. Okay, so before going into the depth, so my main agenda is to make this session a more interactive one. So I will recommend that every participant who is participating in this meetup. So I will just ask some few questions to see like how people know about the quantum computing and these new trending technologies like LLMs and all those things. If I just ask a question to everyone, have you ever heard about the term like quantum computing before, or anyone can tell me about what is quantum computing? So, if anyone can tell me about that, that's a great thing. Yeah. Maybe you can use your chat sections, or maybe if you want, you can unmute your microphone and let us know about that. Okay, so no problem. So I will just explain you about the quantum computing. So quantum computing is a type of computing which actually takes the advantages of principles of quantum mechanics. So maybe if you are in your studies time in maybe plus one or plus two or maybe in engineering, you have heard a lot about like quantum computing principles, which actually deals with the behavior of small particles on a quantum level. So basically, we actually heard about the term atom. So everything whichever we see in our universe or maybe on our daily life is actually constitutes with atoms, and atoms consist of like electron, protons and neutrons and the subatomic particles at the core of that atom basically. So these particles are actually known as the quantum particles. So basically quantum mechanics actually deals with the motion and their behavior of like how those subatomic particles actually behaves in real scenario, and how their properties actually differs and varies in different particles and changes the behavior of the things that we see in our daily lives basically. So in quantum computing we actually try to implement those kinds of principles in our normal computing to see like how the things can be changed in quantum using the quantum computing, right? And the next thing is like about the AI. So AI is a field of computer science which actually provides a human-like intelligence to the machine, so that machine can perform some task by itself without the need of any human intervention. So nowadays you have seen a lot of things like self-driving cars. The cars are driving by itself without the need of any driver. Or you have seen some for example chatbots which are providing some responses, very great responses, without the need of any back-end human being who is providing responses. So all those things are doing machine started doing by itself, right? So this is a kind of a AI which actually provides a human-like intelligence. So what exactly means human-like intelligence is like machine can be able to reason, to solve the problems of a human or to understand their natural language. So for example, whatever we are talking in English and Hindi, so machine will be able to understand all those things and to understand the overall context and then provides some intelligent answers or maybe some solutions based on your problem statements. Okay, so this is actually a purpose of AI that currently right now different models and things are doing. Okay, and next come to the LLMs basically. So if I just talk about like what is LLM, so LLM is actually a part of a AI basically, which actually deals with the large language models. So large language models actually take the advantage of natural language processing based models such as GPT-3. So nowadays you have heard about a term like Chat GPT or Google Gemini based model. So basically these models are actually based on those generative pre-trained transformer based models. So this is actually the core of those models which have the capability to understand the overall context of a human question or query and providing the response based on the context that the machine is actually understanding. So these models have the capability to generate the answers based on the questions it provides without the need of any dictionary or any rule based kind of system. Okay, so LLM basically generally LLM we generally use for completing machine translation, for question answering, for chatbots, or you can also use for generating some codes or maybe some solutions based on your problem statement. So that is a all about the basics. So if you are not familiar with all those things, so basically the purpose of providing all those information so that you will be just familiar of what is going on in the later slides, right? So now, before going into the depth of today's session, so it is very important to understand the things in depth, like what actually quantum computing is and how we actually integrate the quantum computing principles into our classical computers, right? So basically, quantum computing is, as I told you, like quantum computing. In quantum computing, we just normally constitutes a principles of quantum mechanics that we usually see in our like physics or atoms. Okay, so basically, what is exactly the major difference? We first need to understand those things. So basically, if I just talk about a classical bit, so a classical bit is a normally a zero or ones, which normally current computers are actually users, which we usually called it as a binary language. Okay, so binary language actually consists of zero or one, on or off states basically. Okay, so in quantum computing, we just use a three states, which we called as a qubits. Okay, so in qubits, we have three states. One is zero, second is one, and third is like zero or one, which actually falls between zero and one. Okay, so we can say like a atom can be in zero state, it can be in one state, or it can be in both states at a time. Okay, so this is all about a qubit, which actually creates a major difference in classical computing. So in classical computing, we have two bits. So basically, we have two is to power n combinations for to solve any problem. But if we talk about a quantum computing, then a quantum computing can see the things in a three states, zero, one, and zero, one itself. So that means we have 3 to power n combinations. So that means it can provide much more combinations it can solve at a time. Okay. Second thing is it can see the things in a more detailed way, which current classical computers are not seeing. Okay, and third thing is like it can provide some parallel calculations as well, because now it can see the things in both states. That means it can see each perspective for any incident or any event that is happening inside a quantum computer. So that's why these days researchers are focusing more on implementing those kinds of technology. Okay, so this is a major difference that is happening right now. Okay. So now, if I just talk about like how we are actually implementing those quantum bits into a quantum computer. So basically, a quantum, according to the quantum physics, a atom can be in two states basically. So this is known as a quantum superposition. That means like if we have a atom in any system, any physical system, so that atom can be in two states at the same time. That means if I am a human, or consider me as a atom. Okay, so I can be in India, and I can be in USA, I can be in London, or maybe I can be in Bangladesh at the same time. Okay, so that means we can actually implement all those states at physics. So quantum superposition, the same part to understand, because if you are not understanding these things completely, then you will never get the idea like how those quantum circuits or quantum computers are actually working. So this is a most important phenomena that we you need to understand. And second example, what we can see is, so for example, if you just toss a coin, okay, so according to a mathematics or a normal classical computing that you normally see, so when you flip a coin, you can just say like a head come or maybe a tail comes. Okay. But what if I just say you, when coin is flipping in a air, so at that time when it was not fall on the ground, so during when it was in air, so it was flipping in both states, like 0 or 1, head or tail, both states are coming simultaneously until or unless it just fall on the ground. So when the coin is fall on the ground, then we just come to a conclusion like tails comes or a head comes. But before it has not fall on the ground, it was in both states. So quantum computers actually work on the same phenomena, like until or unless any state is measured, the qubit the bit is in both states right now. Okay. So it is working on that kind of principle, which is known as quantum superposition. The second most important thing that we need to understand is quantum entanglement. So quantum entanglement normally says, according to a physics. So for example, if two atoms or maybe two particles that are separated to each other at a very distance. So infinite distance. So infinite distance can be a one end of universe, basically. Like if one particle has a value according to a quantum superposition, so their states can be a reverse of that first state. So if one atom has a value of like for example 1, so second atom that is on the another end has the another value, maybe this is called the quantum entanglement. So for example, here in this example, it is represented as a red color. So at the second point, the same atom is represented as a blue color, which is the opposite of that. Okay. So this is all about like quantum entanglement and quantum superpositions. So basically a quantum computer, if anyone asks you like how quantum computer works, so quantum computer normally works on these two type of principles, like quantum superposition and quantum entanglements, right? Now, if I just tell you about like how it actually creates a difference as compared to like classical computers, and where we usually use these type of things, or what kind of problems we usually solve by using quantum computers. Okay. So basically nowadays researchers are using quantum computers for optimizing the problems. So for example, if you consider, if you have a problem that can be possible, that has a like multiple solutions can be possible, and you need a system that can reason or provides a multiple solutions and then provides a finding the best solutions out of that. So that kinds of solutions we normally called as a optimization problem. So for example, we need to, for example, consider a graph where we need to find a optimized path. Okay, so there can be multiple paths different type of computers can provide, but finding the best route or finding the overall supply chains, so we can use quantum computer over here that can process all those whole world information in just fraction of seconds and provide a multiple paths or multiple best way. So if you just feed all those data into a existing supercomputer, so maybe it can take a years to process that information. Okay, but quantum computer can solve all those things in fraction of seconds or maybe in minutes. Okay. Second thing is like we can also use in AI, like that is also a part of our today's session. So we can also accelerate the process of machine learning. So for example, our current models take a lot of time to train or maybe to inference. So by using the quantum computing, we can fastly process that information and train our models speedily. Okay. Third, we can also use quantum computing in like quantum machine learning. So nowadays some different concepts are there. So basically researchers are now integrating quantum computing principles into existing machine learning approaches. So nowadays you have seen like support vector machines and neural networks. So now researchers have developed quantum support vector machines and quantum neural networks that is based on that is using the existing resources. like you are using. So they are not specializing in using the quantum hardwares. It was just uses the same concepts into existing neural networks to speed up those processes. Okay. And then you can also use to safer your IT and cyber systems. So basically you can build some unbreakable algorithms that can encrypt your data. So basically for cryptography and security, quantum computing has that kind of process to make safer your systems. Okay. And third thing is like last thing is like where you can use is like for example, if you need to do any discovery where it requires a lot of reasoning or maybe kind of a process that a human brain can do. So you can also use those things in discovering. For example, in drug discovery, you can use that uh, quantum computers as well. Okay. So if you just heard about that term like a coffee atom that we need to actually simulate. So in a normal scenario, if we just feed that a coffee atom into a normal supercomputer, so it can take 5 years to just to discover like what can be a possible outcome. But quantum computers solve that problems in just 1 minute. So that is a major difference. That's why nowadays researchers are focusing more on those kinds of things. Okay. So these are the advancements of using quantum computing and classical computings. Now if I just talk you about the large language models, so previously you have just heard about the quantum computing basics. Now you just need to focus on LLMs so that you can actually correlate that information like how we can actually use quantum principles with LLMs. So if I just start with LLM, so LLMs are basically advanced NLP based models which are powered by like deep learning techniques. So if I just talk about the basic building blocks of LLMs, so any language model is just to make of these 5 steps basically. So first step is tokenization. So tokenization is nothing just to convert your words in a sentence into a normal digits so that computer can understand, because computer is not able to identify like what is the meaning of hi or what is the meaning of xyz or any kind of words. So basically computer needs to convert those words into a normal digit form, and then at a machine level those words those tokens can be converted into a machine level language like zeros and ones, and then understand better. Okay. And second thing is like embedding. So embedding actually consists of a like a vector which actually stores the value of tokenizations. So basically what value it is using to represent any words into a number. So embeddings consists of those data, and attention usually consists of like it actually a brain of a large language model, any model. Okay. So basically attention layer is to provide how a model can predict the different words or maybe the things using the attention layer. Okay. So basically attention layer takes the data from the tokenizations and embeddings, and then it try to use some feed forward neural network to predict the next words that is happening over there. Okay. So this is the part of like attention layer. Then pre-training is basically used. So in generally in large language models, so for example various tech giants like Google, Microsoft are using a large data, for example a generalized Wikipedia data or Google search engine data to train a model over there. So it just train a model so that other people can use those models in a with a very good accuracy. So you don't need to train the whole data by your itself. Instead of, you can use that pre-trained model over there, and it can provide a good accuracy to you. So basically if you just want to train your model onto your specific data, basically, so you just need to provide a few samples of your data according to your basic requirements in your organization, and that model can give you a great accuracy. So this is the concept of like pre-trained models. So you can go with like open AI, you can use a Google Gemini API over there that can solve that kind of purpose for you. Okay. And transfer learning, so transfer learning is basically a concept of transfer knowledge from one task to another task. So basically in large language models there are different type of tasks that we assign to a machine. So basically the purpose of to transfer their learning from one task to another. so that you can train your models on other tasks as well easily. So that is the concept of transfer learning. So these are the basic components of any LLM based model. Okay, so if you see any LLM based model, these are based on these type of concepts. Okay, so if I talk about just a key features, so basically key features include like those models have the capability to understand the overall context, the complex language structure. So for example, if you are talking in a complex language, basically you are using phrases or maybe idioms. So LLMs can have the capability to understand those things, and it can also understand your different type of like slangs and all those things basically. Okay, and we can use it in various diverse applications. For example, we can perform machine learning translations, we can use summarizations, or we can also include some text completion. So we can maybe write a story, we can generate some codes and all those things that you generally see in your daily life. Okay, so this is all about like whole LLM. Any question from anyone? Okay, no problem. So if I just talk about like what are the challenges in classical computing that are currently we are using in LLMs, and why we need to integrate a quantum computing over here. So right now we are seeing like those models are very powerful, like ChatGPT, like Google World and Gemini. Those are very powerful model, and it is providing results as we are expecting from any AI models. But still, there are some challenges. So first major challenge is like to handle these computational requirements. So currently, the models, if we want to train our own LLM based model, so we actually requires a large number of computing resources. So maybe we actually need to build a whole data center for that. Okay, and we need to provide a large number of data, and we need to build a complex mathematical computations, which is very tricky and complex for any startup organization, for any educational institute, or for any individual. Okay, so that's why this is the main reason, like still LLMs are only created by tech giants. For example, Google, Microsoft, Facebook, Amazon, these companies are actually creating. So that's a very huge challenge, like how we can train our own LLM by itself. Okay, and second thing is like these models needs a very large time to train on a data. So for example, before launching a chat gpt or Google world model, so Google was working from last 15 or 20 years to actually create a model. So from like 2000, in the starting of 2000s, Google has started work on these kinds of things, and finally it was launched in 2022 or maybe 2023. So after 22 years of time, it was taken by these companies to actually create a whole model, because they are training those models on a whole world data. It's not just a task of like only a one Excel file or one CSV file. It's just a task of capturing whole data from the whole world, and then you need to train that model. So basically, it's a very time consuming process right now. So that's why it is a very big challenge right now. And third is like scaling those classical computing resources for large language models becomes increasingly challenging. Okay, so basically when you just create those models, those heavy models, so sometimes it was a very difficult to deploy those models on a cloud, so that it can actually meet the demands of different type of peoples. Because at a time, uh, in the whole world, billions of users are right now using Google Bard model. Okay, so think from that perspective, like how we need to scale that model so that it can fulfill the demands of each user at a time. So this is a very challenging part, right? So now if I talk about like how we can integrate the quantum computing in LLM so that we can solve those kinds of problems. So basically, as I explained you about the superposition and entanglement principles, so basically those kinds of things can actually perform parallel computations at a time, which can offer speed up in the model training process, and we can also influence those tasks for large language models, right? Second thing is like researchers are now exploring quantum algorithms to address specific challenges in NLP. Okay, So that can offer some potential breakthrough through optimizing LLMs beyond the capability of classical computing. So basically, now researchers are working on the same concepts that current classical computings are providing, but they are just tuning those networks using quantum principles. So basically, if you heard about that term like transfer learning, basically, right? So now researchers are solving those kinds of things of transfer learning using a quantum principle. So now they have built some algorithms which is known as QTL or QML, like quantum transfer learning or quantum machine learning. Okay. So basically, quantum computing we generally use to process vast amount of data at a simultaneously time. Okay. So it actually uses a kind of a concept of parallel computation. So it is well suited for a task like pattern recognition or to find a context from a language for large language model. This is a very important part for any LLM. Okay. Now, if I just talk more about like what is quantum transfer learning, QTL. So QTL actually takes a concept from a classical machine learning, where the purpose of transfer learning is to transfer knowledge or information from one task to another. Okay, so as you can see in that architecture that I have built basically. So basically, it's very similar to a normal neural network that you usually see. So here the main difference is like how we are actually processing the information over here. So in a normal transfer learning concept, we just use some LSTM cells, like long short-term memory cells, to process the information. Whereas in quantum transfer learning, we just normally use that variational quantum circuit, which is known as VQC, basically. So in VQC, where basically there are some parameterized circuits over here, okay, that can transfer their learning from one cell to another cell, okay, and it can also process the information simultaneously in both states. So as you can see, I just feed the input as a it's a 4 qubit quantum circuit over here. So I just feed 000 to each qubit in my network. So basically, I just applied a quantum superposition principle that I have explained to you. So at a time when I just feed that information, so each qubit is giving me output of like 0 and 1 at the same time. Okay. And then I just feed that information into my VQC basically. So if I just zoom that for you, so you can see like different type of possibilities that can be possible at a time basically. So these can be the strings that model has processed, and then I just again apply a superposition over here to find some more possible outcomes. So each qubit is now giving me 16 possible outcomes for a specific string that I have just provided basically. So okay, let me just share me again. Let me know if you just can see again, right? Okay. So I was just explaining this architecture to you, like what is the major difference of like quantum transfer learning in like normal classical transfer learning, basically. Okay. So as you can see in this architecture, each qubit is giving me after passing the outcome from the hidden layers, it is able to giving me 16 possible outcomes for each qubit. Okay, and then I had just integrated that quantum inference layer, for the purpose of that is to provide best optimized solutions for my outcome. So if I just give a out input as a 4 zeros, so it can provide me like 64 possible combinations. So as a researcher, you can now get a proper idea like how to solve a problem in different ways. Okay, so this is something like a human brain can actually work. So for example, when if someone asks you about like I need to go to a Delhi, so what can be the possible way? So as a human, you can provide n number of solutions, right? But when you ask about a machine, so machine usually gives you some one or two solutions. So quantum computing can also reasoning the things like a human brain that is happening right now in this architecture. Okay, so this is the concept of like quantum transfer learning. So now, if I just talk to you about like how we can implement, or what is the main major roadmap that we can follow to implement quantum computing in LLMs. So basically, first we need to just we need to encourage people to for research and development in in these algorithm developments. So basically, we need to design some quantum algorithms, basically, such as quantum transfer learning and other things. So we can also maybe train some of our own models like QBERT or maybe QGPT as well in future as well. That can specifically tailor the needs of like natural language processing. Okay, so this is the one step. Second step is like in quantum hardware development. So basically, right now the quantum hardware are very limited and are only created by some tech giants like Google, IBM, or maybe Microsoft. Okay, so we need to enhance or maybe collaborate with like those quantum hardware developers who are directly working on those hardwares, and then we can actually implement those models more efficiently. And third is like integrations with classical systems. So for example, currently whole world is using the same computers, okay, like servers or maybe laptop or computers. So basically, we need to integrate those systems in a more seamlessly manner so that we can actually follow those kinds of things and work efficiently. Okay, and then we can use some pilot quantum language models as well. Okay, so we need to conduct some pilot projects to implement quantum enhanced language models on smaller scales that is used to evaluate their performance, scalability, and practicality before full scale deployments. Right. Okay, so now it comes with like some integration challenges as well. So uh, currently we have talked about all those concepts and things, but it seems very easy. But in real, these actually create some challenges as well, because sometimes when we just try to integrate those quantum computing principles with existing LLMs, so it will actually require some compatibility issues as well, because the current models are usually using bits concepts like zeros or ones. Okay, so they are dealing with those kinds of things. So we need to first uh, change all those concepts. We need to just feed the qubits concepts inside their architecture, so it can create some compatibility issues as well. And second thing is like we can develop the algorithms, but to run those algorithms, we sometimes need some quantum ready software or maybe some quantum hardwares as well to process those kinds of information. So that can also be a one challenge. Okay, and the third thing is like current quantum hardwares have limited qubits. For example, you have heard like Google has built a 74 qubit of system, IBM has built like 500 qubits of system, right? So when there will be demand of different type of system, then this can create some problems or maybe some coherence times as well. Okay, so these can be the some challenges that currently we are facing. So that's why researchers are limitedly work on those kinds of things. And we also need to consider some ethical considerations. Okay, so sometimes as a quantum algorithms sometimes actually provide some inaccuracies as well. Okay, so there will be some data privacy and algorithmic biases may be possible. Okay, so that's why we need to consider all those things into considerations while working on those kinds of things. Okay, and then we need to maintain a proper balance between quantum capability, and we need to respect privacy and security considerations in development and deployment, which is a very important part. And we need to also follow those kinds of same things in AI development for any model as well. Okay, and we need to provide some transparency and explainability. So current quantum models provides the results which are very very complex to understand for a normal human being. Okay, so we need to work on those algorithms to provide a more explainable result so that everyone can understand those things in a more better way. Okay, because only some experts or maybe physicists can now understand what quantum computing is actually producing as a results, because those results usually consist of some qubits concepts or maybe some physics concept, which is a very difficult thing to understand from a normal developer. Okay, so these are some ethical considerations we actually need to follow. And now if I just talk about like what can be the future, or what can be the future of LLM with quantum computing. So basically in future we can see some models in LLMs which can provide the same level of accuracy or maybe better accuracy that right now our AI models are doing, but that will require more enhanced processing. Okay, basically. So, for example, we can see now, like if any Google Bard or Google Gemini model takes 22 years of time in training part. So maybe we can see like after quantum computing integration, we can see like the same level of same amount of data can be trained in just 10 minutes or maybe just in 1 year. So that can also be possible. So it can actually accelerate their training and inference process. And we can also see some innovations in quantum language models. So we can now in future we can see like a model can be able to reasoning or to understand or think like a normal human being. Okay, so we can say like in computer history, in like 5 or 10 years later, we will see like a robots which will like a normal human beings. Okay, so we will not find any difference in terms of like their consciousness or maybe their reasoning process. That all will be similar like a normal human being. Okay, so this can be an innovation that will be possible using quantum language models. Okay, and third is like their unprecedented computational power. So again, quantum computing has a potential to process all those information parallelly, basically. So we can get some unprecedented computational power. So now if I just come on the in conclusion part, basically. So if I just talk about like conclusion, so basically the marriage of quantum computing and LLM actually promises a transformative impact on language understanding. Okay, so our LLM based models will be more contextually aware, and it will provides a more efficient large language models which can have more capability. So maybe in future machines will be able to understand the deep context or maybe some hidden meaning of their sentences, so which I believe in current models are actually lagging. So these kinds of things we will emit in next future versions of those models after integration of quantum computing, right? And quantum computing has the ability to redefine computational boundaries. For example, it can handle more complex linguistic tasks with enhanced speed, precision, and scalability, right? So this is all about like today's session. So now I'm just going to showcase a shorter demo. So for example, if any one of you want to start your quantum journey, or if you feel like it's an interesting field in future, so maybe you can start your quantum journey from over here. So here in this code demo, I will just show you like how you can actually use quantum computing principles in a normal neural network. So normally you are familiar with bidirectional neural network. So here I am just going to show you like how you can create your own quantum circuit and build your own quantum like QCNN, for example. Okay. So first of all, you just need to install those dependencies. For example, you need to install the TensorFlow. Then this is a library that was introduced by TensorFlow at Google. So this is a TensorFlow Quantum. Okay, so you just need to install import those libraries. Okay, and then it will create a quantum circuit for you, which is a part of like QCNN. So here it is a very similar flow that you generally see in your normal neural network classes, basically. Okay, but here as I mentioned, like quantum transfer learning concept as well. So where we just added a qubits over here. Okay, so these actually represents a qubit in the first layer. Okay, and these actually represent a quantum gates concept. Okay, so when you will just take a deeper dive into a quantum computing principles in more details, so you will easily understand like what these layers are actually doing. So basically in this layer we just superposition those quantum bits, basically. So here it can go into a 0 or 1 at the same time, and then we just added a QVC, like a quantum variation circuit over here in different qubits, and then it is able to provide me a CNN results that a normal CNN model is actually predicting. Okay, so here to implement this whole architecture, here is a code. Okay, so here is a code, basically. So if you just going to run that code, it will create some qubits for you, and then you will see the outputs like this. Okay, so this is the overall architecture, like how this quantum circuit is going to work. Okay, and now if I just going to show you a whole demo of like how quantum transfer learning is actually working. So for example, if I'm just going to run this code over here, so it will just first install all those dependency and import these libraries. So it will usually take just 1 or 2 minutes, right? Maybe my net is a bit slow, so it is taking some time. So basically, once you get install these libraries, so you can run this class. So basically, I have just included a quantum circuit over here. Okay. So basically, the purpose of that quantum circuit is to find similarity between different sentences. Okay, using a quantum transfer learning. So for example, if I just give two sentences to my model, so how much they are actually similar, or what kind of unique words are used in that. So we will predict that system. So here we are using 4 qubit circuit. So it's a 4 qubits quantum machine learning, quantum transfer learning circuit, basically. Okay, so first I just define these layers in that model. Okay, and when I just run this model over here, so this is used to create a architecture for quantum transfer learning, this class. Okay, and the second class is to train that model, basically. So here you can see, if I just going to tell, like, uh, how it will work. So here we will just feed those sentences into our corpus. So for now I have just to use only 3 sentences to train, like how it can get the results. Okay, just to show. So because it usually takes some time to train that models, that's why I just use these 3 sentences over here, so that you get the idea. So once you start training that model, so for example, I just given here like 20 epochs, or the size of like embedding dimension is 32. So basically you will see like the model has started the training. So you will see like how it will actually reduces the losses after some time. Okay, so it will also be able to find the different words, unique words that are used in all my 3 sentences over here. Okay, so this actually tells you about that. So it tells me about like 34 unique words are used in this vocabulary, and it also let you know about the data, like how it is actually going to understand the overall context by replacing different sentences. So for example, it is just telling me like this tutorial will you throw it walk. So walk is the unique word that can be contextually important for there. So it is actually telling you about that. And after that, it also tell me about that the similarity between the first words in that I use. So currently I just tell you about, currently I just told my code to tell the differences between these two words. So basically it will be able to tell me the differences, like the difference between NE and R are minus 0.14%. That means it is not related to each other. Okay, there is no similarity. So these are very far from each other, basically. So these are some ways which you generally follow to use quantum transfer learning concepts in your normal codes as well. And here you can plot a normal graph to see like how on each epoch how it is going to drop, basically. Okay, so right now you can see like the losses are dropped from 3.6 to 3.1. So basically there are losses over here. The main reason is because we have provided very less sentences for that training part. So if we increase the number of sentences, maybe 100 or thousands, so those losses will be more or less. Okay, but this is just a demonstration, like how you will in real life, how you can use these kinds of concepts. So that's the thing that I just want to show you in this code demo. So I just also added these code links in my, like at the end of this session presentation, so you will get all the idea from there as well. Okay, so this is all about like today's session and overall code demo. So I hope you get some idea or the things from there. So now it's time for some questions or maybe some suggestions